Today's lesson is about graphing transformations on a coordinate plane and finding patterns between the equation you're graphing and what it looks like on your paper. So first off, copy down this definition. It's important that you understand the idea of function family. This is actually a building block of an idea that you're going to use quite a bit next year in Algebra 2. A function family is a set of functions or equations whose formulas have a similar form. The parent of the family is the equation with the simplest form. Here's an example of a function family, the linear function family. There's plenty more, but these are just a couple basic ones. So anything that has an x to invisible power of 1 in it, and no other x's with different exponents than that invisible 1, is going to graph into a line. That's why it's called a linear function family. And these are very familiar because you've been graphing lines for years. So the parent function is the very simplest line possible, y equals x. You know how y equals x is the same thing as y equals 1x plus 0? So your b value, your y-intercept is 0, and then your slope, your m, is 1 over 1. So you go up 1 over 1 from there. Pause here and think back to what you've learned about graphing lines in the past. Graph the next two lines. And check your graphs. For the second one, you had a b value of 3, y-intercept of 3, but the slope is still 1 over 1. For y, you had a y-intercept or b value of 0, but the slope is negative 1 over 1, so we went down 1 over 1. So this is all very familiar to you. The reason why we're going over it is because today you're going to take some of the patterns in the equations and how they affect the graphs, and you're going to apply it to function families that are not linear. For example, the x squared family, the quadratic family. Y equals x squared is the parent function. It's the simplest version. You may or may not have learned how to graph y equals x squared last year in algebra. It kind of depends on whether your teacher had time to go over it. So I'm going to quickly teach it now. To graph something like this, let's start with a table. If you plug in -2 for x into x squared, -2 squared gets you 4. Remember, negative times negative cancels out and gets you a positive. And make sure when you're showing your work, you have that -2 in parentheses to show the negative is part of what the number that's being squared, being multiplied by itself. So if you take your t-chart of points, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and graph it, it looks like this. Connect those points and it makes kind of a narrow U shape. It's not really a V, it's more of a U. That type of shape is called a parabola, and you'll be working with those quite a bit next year, so it's a useful thing to get a preview of now. If we repeat that process for the next one, if we make an XY table, plug in -2, -1, 0, 1, and 2, you're going to notice how the shape you get when you graph those points is the exact same. It's still parabola. It's just located higher up the graph. Now here's a pattern I want to point out. You know how y equals x squared, its vertex point, the point where the U turned, was at the origin 0, 0? Here, the origin is at 3 on the y-axis instead. I want you to compare that to the graph you did above for y equals x plus 3. You notice how that moved your graph up 3, so the y-intercept was 3 instead of 0, like the parent function? I want you to notice the same pattern holds true for other function families, like y equals x squared. If you add 3 at the end, it just moves your whole graph up 3. Now, that pattern is going to hold true for all sorts of function families. Instead of x squared, let's say it's an x cubed, or even a square root of x. So if you have a plus 3 at the end, it's going to take whatever the parent function is and move it up 3. Last one, xy table for y equals -x squared. Notice how when you're plugging in -2 here, the -2 is in parentheses, but the negative here is outside of them. So -2 squared is 4, but there's a negative outside parentheses, so your final answer is -4 there. Go ahead and fill in your table. graph those points and connect it, I want you to notice how y equals negative x squared got you an upside down parabola. I want you to also compare that to the line graph you did above that of y equals negative x. You know how negative x was basically the same graph as your parent function y equals x, but flipped upside down so the slope was negative? That's going to be patterned across all function families as well. If you start your equation with a negative, it's going to take the original graph, but flip it upside down. And that will be true for all sorts of more complicated function families than y equals x squared. We'll go over one or two more later. So to summarize the rules of how transformations happen on graphs based on changes to the equation like a +3 or a negative in front, a negative coefficient, like y equals negative 1 x squared, reflects the parent function across the x-axis, y equals x squared here, and then you could see how y equals negative x squared is just a reflection across the x-axis. A constant, a number without an x, that's added at the end of a function shifts or translates the parent function up or down, and that's another rule you discovered in your graphing earlier. Y equals x squared plus 3 just translated the whole function graph up 3 units. And it's pretty intuitive, kind of common sense how the directions work. Positive numbers added at the end shifts it up. Negative numbers added at the end shifts it down. Here's a quick example of that happening with a more complicated function family that you're going to deal more with next year. So this dotted green line, that's actually the original graph of y equals square root of x, which you'll officially learn next year. You won't see it too much this year. I just want to point out how adding 2 at the end just takes that graph, and it's the same shape, just starting at 2 instead of 0. Now there's 2 more rules, and these you are a little bit more new. These you did not discover with the graphing because they're a little bit more complicated. Fill this in. A constant, or a number without an x, that's added inside grouping symbols next to the x, like grouping symbols like parentheses or absolute value sign, something like that. What that does is it translates or shifts the parent function left or right instead of up or down. A positive constant shifts left and a negative constant shifts right. So here we have absolute value of x plus 4. Absolute value is a function family we're going to go over in just a moment, but I just want to point out how having a plus 4 inside the grouping symbols shifts the graph 4 left from the origin. And we'll talk more about that in a moment. Now, there's one last type of transformation that we did not talk about, how it appears on a graph based on the equation. We've talked about reflections, we've talked about translations, up, down, and left and right. Now we're going to talk about dilations. Having a number in front of your equation, a coefficient other than 1, causes a dilation of the parent function. And that coefficient is essentially your scale factor. If a coefficient is bigger than 1, it's an enlargement. It stretches your graph up and makes it narrower. If your coefficient is less than 1, it's a reduction. It flattens the graph and makes it wider and shorter. So here's a quick example of that. The dotted gray line is your original parent function y equals x squared, a basic parabola u, starting at 0, 0. Now, putting a coefficient in front of the x squared doesn't change the origin. It doesn't translate it left, right, or up or down. It still starts at the origin. But because the coefficient of 4 is bigger than 1, it's an enlargement. It's a scale factor of 4. Basically, every point starts 4 higher than it would otherwise. The points that would have been at 1, 1 is now at 1, 4. So it makes it a taller, narrower, more quickly growing function. But if I have a coefficient in front of the x squared that's less than 1, like 1/4, it takes the original parent function in gray and it flattens it and makes it wider. It's growing more slowly. Basically, each point is starting at 1/4 the height that it used to have. If the parent function had a point at 2, 4, instead of having a height of 4, it has a height of 1, 2, 1. Now, we're not going to deal too much with the graphing of dilations based off of a formula this year, but it's important to know because it's a big idea for a lot of Algebra 2